Hey, welcome back to the Game Dev Engineer Super Duper Study Sheet. Today, I actually just added this section. I moved it up a bit for semaphores. I just wanted to show you an implementation so that you could read over it and just get a better idea of kind of how semaphores work and what that notify and wait function look like. But I wanted to talk today about mostly atomicity and how it applies to lockless lists. So a few notes here. Okay, so some stuff is naturally atomic, and that has to deal with what the processor bus is. So an operation is atomic if the data is aligned and the bus is at least as wide as the type being written or read. And the reason why is because when you scoop up the value, if you completely grab it in one shot, or you completely edit it in one shot in one system call, then you're going to be able to get it done before the processor moves on to anything else. So in other words, if it's one operation to do because it's so small, then it's going to be done in one operation. So no one's going to be able to jump in between several operations because there's only one. Okay, so on an x86 system and x64, um, we have here that there is no guarantee that reads and writes larger than 8 bytes are atomic. But under that, we do have the guarantee that if you're going to be just editing a small number, you're going to be safe. Likewise, with reordering, the order of reads and writes might be changed by a compiler. And so to combat this, we can use this paradigm called the read acquire and write release barriers, which I don't go into too much depth here because I haven't really been quizzed on it. But it's something that I'm currently still working on studying. And then in programming, the way that we make lock-free data structures is by first removing the locks and then redesigning the data flow to use atomic APIs. So we're going to talk about that in a second. But just in general, locks are nice compared to lockless implementations, and because locks are a little easier to think about, and we can context switch, which can be really useful while we're waiting. Okay, so let's talk about whether or not these things are atomic or not atomic. I think this is from the official Microsoft Health page. But basically, this implementation is not atomic because the D word is not natively aligned. Here we have three separate operations which are all hidden within the pre plus plus here. This would be an atomic write if the global is under 8 bytes, 8 or less bytes, and then this would be an atomic read. But again, you have to worry about the order of the reads and writes changing. If that's relevant for you, you need to be concerned about that. And if the order matters, then you're going to need to make that a critical section, which is locked by a mutex or whatever. Okay, what else here? So this is a safely lockless increment using the interlocked XXX. So the idea here is if you call the method interlocked increment or interlocked, whatever, then what you're going to be able to do is safely do a lockless increment on a non-atomic number. So this is another way that you could do that using this sort of thing that's defined for C++. Okay, so let's talk about the lockless APIs. And the reason why we want to start talking about these is because I have gotten the interview question, which is, please explain to me how you would implement a lockless list or a lockless stack. I haven't figured out the examples for lockless stack yet, but I've explained the process in pretty good depth right here for the lockless list. But again, the principle here is, as I've said before, you're simply going to be first removing the locks and then using these atomic APIs. So let's talk about what those APIs are. Here are the C++ provided lockless atomic APIs, which are basically implemented for direct hardware support that support atomicity. So the first is CAS, which is right here. It's compare and swap. And so you can read in greater depth this wiki article. And then this one, FAA, is the fetch and add. And then I think there's one more, but it's pretty much never used. At least I haven't seen it used a lot. Yeah, I can't. Yeah, there's one more that comes up in the. No, I can't find it. But there's one more, but it's not relevant for us because CAS is just as good. However, you do need to be aware of this one problem with CAS. Well, first let me explain CAS. So CAS, compare and swap, is basically a method, and you provide a pointer, an old value, and a new value. And the way that it works is the pointer is pointing to something that has a value. If it's the old value, then replace it with the new value, and that's done in a single atomic operation. However, If the pointer is pointing to a value that is not the old value, then don't replace it. And this method returns usually a bool telling you whether or not the replacement was successful or not. And this is actually the implementation right here in sort of like a pseudocode format, right? It's not written in C++. It's a assembly probably. FAA, fetch and add, the way that works is it will basically it just gets you the value address and then it increments it. So it's basically like a plus equals operation for the increment, and then it returns the new value. So that's basically how fetch and add works. Okay, great. And so there's one concern for CAS, which is ABBA. And what happens there is a value may be changed and then changed back before the comparison. So this probably isn't going to be relevant for us, but basically the concern is the whole idea is that you're going to say what is the old value and only replace it if the old value has not changed. However, the old value may have changed and then it may have changed back before this process runs. And so that's essentially what the ABBA problem is, and there's some creative ways that, system architects can combat it, but by noting certain things. And so it's probably not relevant, but if you want to look into detail, you could check it out there. Okay, so now to my interview question, where this person asked me to implement a lockless list, and I cried because I had no idea how to do it. But that's okay, because I'm not going to cry anymore, because I have since learned. Okay, so basically for the lockless list, there's two interesting methods, insertion and deletion, and both of them are going to use CAS as a paradigm in order to make the implementation. Now, this implementation actually comes from a really good paper, which I think I've linked here. Yeah, so this is an academic paper by Timothy Harris from Cambridge. I don't know when this came out, but it's pretty much, I see it referenced all the time now, so I guess it was a pretty seminal paper. And almost all the algorithms I'm grabbing are just from the abstract here. I haven't really read all of it. I just needed the front parts, all that's really relevant. So here, when you want to do insertion, what you can do is you can basically set up a new node here, point it to this node, and then in a single CAS, a single compare and swap operation, you can change the 10 to, instead of pointing to the 30 here, to point to the 20, which is already pointing at the 30 because you set it up. So that's the basic principle there. You just do you sort of aim your gun, and then right when it's ready, you switch everything and shoot the shot. So that's kind of how that works. So basically, what you want to do is you're going to take the next element, which in this case would be, you're going to create a local variable called next, and then the current elements.next, you're going to save it there. So this is basically creating the 20 and pointing it to wherever the 10 should be pointing to. Then you're going to, so you're going to take a local variable, next. So this is amorphous. It's not shown in the diagram, but it's going to have the address of 30. Then you're going to create your new element and set it to point to that next. So that's where the 20 is now pointing to the 30. Then in a single compare and swap, you're going to see, hey, is the current element still pointing at that 30? And if it is, then now make it point at the new element. And so that's basically saying, hey, is the 10 still looking at the 30? Okay, if it's looking at the 30, then boom, switch it to the 20 in a single processor operation, and that's going to be insertion complete. And if it's not successful, then you're going to repeat this whole process going all the way back to step 1. Okay, so that's insertion for a lockless list. Unfortunately, this algorithm does need to be memorized. Now let's talk about deletion. So for deletion, one CAS, one compare and swap operation, actually is not enough. We're going to need 2. Now, why is that? Well, it's actually explained really well in the paper through these 3 paragraphs, so you can read it. But basically, the idea here is that you can leave a 10 dangling. So if you want to read that, feel free to do so. It's linked here. But suffice it to say, there is another method that's going to work, and it's going to use 2 CAS operations. So the first one is basically going to mark the node with an X here so that we know no other node should be inserted right after it. And this is what Timothy Harris calls a logical deletion. And so he's basically creating 2 different steps. He's saying, let's logically delete it, and then let's physically delete it. So the first thing that you're going to do is you're going to go through the list and find that node you want to logically delete, and you're going to mark it as logically deleted using the first cast. Now future insertions are not going to be behind it, so you don't have to worry about the 10 pointing to something that's kind of stuck in the chain here. Then a later traversal will then go through, and it's going to delete it using a second cast. And the reason why this is going to work now is because we know that between steps 2 and steps 4, there's no nodes that are added after the 10. So that is the lockless list implementation of deletion. Now, you also might be asked about how to implement a lockless stack. And I haven't yet implemented a diagram or copy and pasted a diagram or figured out the insertion, or I guess in this case it'd be the push and pop for that. But this is something that you should definitely do on your own because you very well may be asked it, and so this is something that I have to add to the guide still. Okay, great. So I think that's going to wrap up this section, and in the next section we'll talk about some of this miscellaneous math stuff as well as C++ information. Oh, there's a lot of fun in store for us. Can't wait. It's going to be great. If this helped you, please leave a comment where you have questions, and I'll see you in the next video.